Everyone. My name is Lablack Mourad from Dalian University of Technology, and I will present to you today our work entitled Long Sequence Model for Traffic Forecasting in Suboptimal Situations. We will start by introducing the subject of traffic forecasting and what are the challenges faced when trying to produce accurate predictions, while being resilient to missing data or inconsistent sampling rates. Subsequently, we will provide a concrete problem definition. Thereafter, we shall describe the model architecture and the preprocessing necessary to achieve lightweight, robust, and accurate spatiotemporal predictions. Furthermore, we will discuss our model performance and compare its ability to provide accurate forecasts on different scenarios to the baselines. In conclusion, we will highlight the contributions presented in this paper. In light of the rapid evolution in sensor technologies and network infrastructures, we are witnessing an exponential growth in data acquisitions. Intelligent Transportation System (ITS) harness this wealth of data to offer a diverse range of services aimed at enhancing our daily lives. Among the various facets of ITS, traffic forecasting emerges as a pivotal component. Achieving precise traffic prediction necessitates a comprehensive consideration of spatial, temporal, and external factors. Traditionally, traffic data has been subjected to pre-processing into two primary data structures: grid-like images and graph-based representations. However, recent years has seen a pronounced shift towards favoring graph-based approaches. These methodologies enable the analysis of traffic dynamics with a non-Euclidean space, allowing for a more fine-grained examination of the data. Consequently, the majority of the contemporary methodologies are grounded in the graph neuron network, encompassing graph convolution networks and graph attention networks. It is worth noting that GNNs typically require the complete graph for proper functioning, a characteristic that often results in substantial memory consumptions due to the quadratic nature of matrix multiplications. Moreover, the transition to high-speed networks technologies such as 5G and 6G introduces a unique set of challenges. These technologies operate on short waves that are susceptible to obstructions, leading to data losses. Additionally, the sensors employed in data collections are prone to power fluctuations and technical malfunctions. Nevertheless, most existing frameworks assume the availability of clean and reliable data to produce high-quality forecasts. These deterministic models rely on established traffic patterns rather than learning the underlying data distributions, posing a limitation in their adaptability to real-world scenarios. In contrast, probabilistic approaches are designed to learn the underlying data distribution and exhibit greater resilience in the face of data quality issues. However, they are notably intricate to train and have seen limited success in forecasting tasks, primarily finding utility in generative applications. In this context, our research endeavors to address the aforementioned challenges and provide a holistic understanding of traffic forecasting in the context of contemporary ITS. Let us define formally the traffic forecasting problem. Generally, traffic forecasting consists of learning a function f that takes h historical time steps at the node eta and produce achieve future time steps for that node eta. However, in our work, we take a probabilistic approach based on denoising diffusion, where we start from a pure normal noise denoted as x hat big N and gradually denoise that signal until producing a clear signal x hat 0. Additionally, we condition this process based on the historical data denoted as x dot. In other words, we learn the function p that given the x hat n noisy signal and the nth Markovian step and the historical data for a node eta, we restore the previous less noisy signal and repeat this process until getting a clear signal. Since this is a progressive process where the model learns each Markovian step individually, we describe the forward process as being a function q that takes a signal xn-1 and produces a noisy signal xn, which is repeated until achieving a pure normal noise. In our research methodology, we address a key challenge encountered in graph-based approaches, namely the issue of excessive memory conceptions. To overcome this limitation, we introduced the concept of a hybrid ego graph which incorporate historical data, neighboring information, and analogous traffic patterns. Consider our objective: predicting the future traffic condition at the target node depicted in red. We approach this task through a multifaceted strategy. We first start by incorporating its historical information. Secondly, recognizing that the traffic at the target node is intricately linked to the flow of traffic to and from neighboring nodes, denoted in blue, we incorporate their traffic data into the graph as well. Lastly, the target node traffic profile is often closely related to nodes that share similar characteristics, such as their proximity to an important intersection, for example, which is represented in yellow. Returning to our illustrative example, the upper chart in the figure underscores the similarity in speed fluctuations between the target node in red and a geographically distant yellow node. Conversely, we also observe that speed reductions in the neighboring blue nodes frequently precede more pronounced speed declines in the target node. To address these observations, we propose a methodology that involves the extraction of the most analogous node using dynamic time wrapping, DTW, and the identification of the closest node are based on the distance matrix. Subsequently, we construct a lightweight one-hop graph which serves as our primary input data. It is noteworthy that the lightweight graph constitutes our conditional data sets, setting the stage for a discussion of our model architecture in the subsequent section. Our model, entitled Spatiotemporal State-Space Probabilistic Diffusion, ST-SSPD, is the approximation function to the reverse process p theta of the diffusion process. Let us begin by elucidating the essence of the diffusion process itself. The diffusion process encompasses two distinct phases. The forward process, denoted as q of xn given xn-1, entails the gradual transformation of the data distribution into an analytically tractable distribution via a Markovian chain. At each step of this process, a small increment of normal noise is introduced. Conversely, the reverse process, also known as the denoising process, is represented as P of xn minus 1 given xn. This phase aimed to recover the added noise, thereby reconstructing a less noisy signal. Our approach to realizing the reverse process hinges upon a denoiser that adopts an encoder-decoder architecture. This denoiser takes as input the noisy signal denoted as x hat, the Markovian step n, and the temporal information tau. It subsequently generates an approximation of the random normal noise that was originally introduced. To condition our denoiser effectively, we rely on the output of a conditioner, an encoder-like module that incorporates historical data represented as x dot and temporal informations, tau. Notably, both the denoiser and the conditioner modules are founded upon our vectorized state space block. This block is instrumental in decomposing the signal into the Fourier domain frequencies, and then reconstructing a new signal based on these frequencies. This element of our architecture plays a pivotal role in mitigating the impact of any missing steps in the process. Looking at the performance of our model compared to popular graph-based approaches, we can clearly see that our model outperforms all the baselines by a large margin. More specifically, 45% on PEMS Bay, 25% on PEMS D7M, and 22% on METR-LA. In order to provide a more comprehensive grasp of the enhancement we have achieved, let us examine the figure on the left side. Given that our model adopts a probabilistic framework, we depict our model's predictions as the confidence interval in green, derived from 10 quantiles. In contrast, the baseline predictions are illustrated as the dashed blue line, with the ground truth represented by the red line. In regions characterized by minimal speed fluctuations, both models exhibit comparable performance. However, during instances of high-speed reductions, notably during peak traffic hours, our model adeptly tracks these changes, displaying a more agile response compared to other models which demonstrate slower reactions. Furthermore, for a comprehensive assessment of the impact of missing data on each model's performance, we have devised a scenario closely mirroring real-world conditions. In this scenario, we have introduced random imputations spanning from 45 minutes to 1 hour, as depicted in the figure on the right side. The gray shading in the figure delineates the areas where data is missing, a condition that applies to both the deterministic baseline models and our model ST-SSPD. Conversely, the orange area signifies the prediction target specific to our model ST-SSPD. The most conspicuous observation is that the deterministic models, utilizing a 1-hour historical window, fail to acquire sufficient information to generate any meaningful predictions within the imputed gray area. Instead, they repeatedly produce nearly identical values with negligible variations. Conversely, predictions made in the absence of imputed data appear to be minimally affected, indicating that the baseline merely incorporates the historical window provided. In contrast, ST-SSPD demonstrates the ability to reconstruct the imputed gray area with a high level of confidence for all 4 imputations. Despite the presence of imputed historical data, ST-SSPD still manages to provide acceptable predictions for the prediction target. In summary, our visualization and analysis shed light on the superior adaptability and resilience of our model ST-SSPD, particularly in the face of missing data, dynamic traffic conditions, and the need for probabilistic modeling. In summary, the ST-SSPD model proposed in this study demonstrates significant improvements over the previous state-of-the-art models, particularly in suboptimal scenarios. This has been achieved thanks to our proposed vectorized state-space module, which was designed to capture long-term temporal information while reducing the impact of missing data. Additionally, we propose to solve traffic forecasting in a probabilistic way, which allowed the model to learn the underlying distribution, which result in a more robust model. Thank you for your time.